Hello friends! Today we will talk about a topic that you hear everywhere. From your smartphone to your TV, it's changing our world. The topic is machine learning, or ML. Many people think it is very complex, something only for scientists in big labs. But that's not true. We will break it down in simple language with easy examples. My goal? By the end you'll have a clear picture of what ML is and why it matters. Join me on this short journey. So what exactly is machine learning? Simple analogy, teaching a child to identify an apple. You don't write a long list of rules like, red round has a stem. Instead, you show the child many pictures of apples. Red apples, green apples, big ones, small ones. After enough examples, the child learns to recognize an apple. Machine learning works similarly. We give a computer lots of data and examples. It finds patterns and makes decisions without explicit rules for every situation. This ability to learn from data is a superpower. In the past, you had to write exact step-by-step instructions, traditional programming, but some tasks are too complex for simple rules. How to write rules to recognize a face in a photo? How to write rules to translate Hindi to English? There are millions of variations. Machine learning shines here. Now that we have a basic idea, let's look at the main types of machine learning. Think of them as three different ways a machine can learn. The most common type is called supervised learning. The word supervised gives us a clue. It is like learning with a teacher. In this method, we give the machine data that is already labeled. For example, we give it thousands of pictures of cats and dogs. Each picture has a label cat dog. The machine studies these labeled examples and learns the patterns. After this training, when we show it a new, unlabeled picture of a cat, it can correctly predict, this is a cat. It learns from the answers we provide. The second type is unsupervised learning. As the name suggests, there is no teacher here. There are no labels. Imagine you are given a big box of mixed fruits. You have apples, bananas, oranges. You don't know their names, but you can look at them and start grouping them. This is what unsupervised learning does. We give the machine a lot of data. The third musketeer is reinforcement learning. This is the most interesting one in my opinion. To build anything, you need building blocks. In machine learning, our main building blocks are features and labels. Let's understand these simple but very important terms. Let's go back to our example of identifying fruits. Suppose you want to teach a machine to distinguish between an apple and a banana. What information would you give the machine about each fruit? You might tell it about the color of the fruit, its shape, its weight, and its texture. These pieces of information are called features. They are individual, measurable properties of the data we observe. Features are the inputs for our ML model. The model uses these features to make a prediction. For house price prediction, features could be the area of the house, the number of bedrooms, the age of the building, its location in the city. For email spam detection, features could be the sender's address, presence of words like lottery or free, whether the email has attachments. Choosing the right features is critical. Irrelevant features mean the model can't learn useful patterns. Now, what about the label? The label is the answer we want to predict, the output. In the fruit example, red color, round shape. The correct answer is apple. Apple is the label. For house prices, the actual price, for example 50 lakhs, is the label. For spam, the label is spam or not spam. The label is what we teach the model to predict. In supervised learning, training data contains both features and labels. We show features and tell the model the correct label repeatedly. Once trained, give new data with only features, and the model predicts the label. Understanding features and labels is fundamental to understanding how ML works. When we train a machine learning model, our goal is to create a model that performs well not just on the data it has already seen, but also on new, unseen data. This is called generalization. However, two common problems can occur during training: overfitting and underfitting. Let's understand them with a simple analogy. Imagine you are a student preparing for a final exam. The teacher gives you a book of 100 questions and says the exam will be based on these. Underfitting is like reading only the first chapter of the book. You haven't learned enough. Your knowledge is too simple. You will perform poorly on the practice questions and fail the final exam. In machine learning, underfitting happens when a model is too simple to capture the underlying patterns in the data. It's like trying to draw a straight line through a set of points that form a complex curve. The line is a poor fit for the data. Now let's talk about the opposite problem, overfitting. Imagine the same student, but this time, instead of understanding the concepts, they memorize the exact answers to all 100 questions in the book. They can answer those 100 questions perfectly, getting a 100% score. But in the final exam, the teacher asks slightly different questions based on the same concepts. Now, the student is completely lost. They fail the exam because they didn't learn the general concept. They only memorized the specific examples. This is exactly what overfitting is. The model learns the training data too well, including all its noise and random fluctuations. An overfit model is like a student who has mugged up the textbook. It performs exceptionally well on the training data but fails miserably when it encounters new data. It has learned the details so perfectly that it cannot generalize. This happens when the model is too complex for the amount of data we have. It's like connecting every single dot in a dataset with a complicated, wiggly line. The line passes through all the training points, but it won't be a good predictor for new points. The goal of a good machine learning practitioner is to find the sweet spot, the perfect balance between underfitting and overfitting, to create a model that generalizes well. So, to understand the balance between overfitting and underfitting better, we need to know about two related concepts: bias, variance. These are two types of errors that can creep into our models. Think of them as two enemies we must fight to build an accurate model. Bias is the error from making wrong assumptions in the learning algorithm. High bias can cause our model to miss relevant relations. It's an error of oversimplification. An underfit model is a classic high bias example. Imagine you are trying to shoot arrows at a target. Bias is how far off your arrows are from the center, on average. If you are consistently shooting to the left of the target, you have a bias. Your aim is systematically wrong. In machine learning, a high bias model is fundamentally limited. For example, using a straight line to describe a curve, it's just too simple. Now, variance is the error from being too sensitive to small fluctuations in the training set. High variance can cause a model to overfit the training data. It pays too much attention to noise and fails to generalize. It changes drastically if you train on a slightly different subset of your data. It's like it has no stable opinion of its own. Variance is how scattered your shots are: left, right, high, low. A high variance model is like this inconsistent archer. The ideal model is like a skilled archer whose shots are tightly clustered in the center. That means low bias, accurate, and low variance, consistent. The bias-variance trade-off is the central challenge in supervised learning. Trying to reduce both errors at the same time is difficult, as decreasing one often increases the other. Now for the exciting part. Let's look at some popular machine learning algorithms. Think of these as different tools in your toolkit. We'll see a simple Python code snippet for each. Don't worry, it's very easy to understand. First up is linear regression. This is used to predict a continuous value, like a price or a temperature. It tries to find a straight line that best fits the data. Python, from sklern.linear_model import, linear regression hash. Predict house price based on area model =linear regression. Model.fit, house_area, house_price. Next is logistic regression. Despite its name, it's used for classification, not regression. It predicts a category like yes or no, spam or not spam. It gives a probability between 0 and 1. For example, it can predict if a student will pass or fail based on hours studied. Python, from sklern.linear_model import, logistic regression hash. Predict if a mail is spam or not. Model =, logistic regression, model.fit, email_features is _spam_label. Then we have decision trees. This algorithm makes decisions by asking a series of yes or no questions, just like in a flowchart. It's very easy to understand and visualize. For example, it might decide if you should play outside based on the weather. Is it sunny? Yes. Is it windy? No. Then yes, play outside. Python, from sklern.tree import decision tree classifier hash. Predict if a loan should be approved, model =, decision tree classifier, Model.fit, customer underscore data, loan underscore approved underscore status. For unsupervised learning, a very popular algorithm is k-means clustering. Its job is to group unlabeled data into a k-number of clusters or groups. It puts similar data points together. For example, it can group customers into different segments based on their shopping habits. Python from sklern.cluster import. K-means hash group customers into 3 segments. Model equals sign. K-means n underscore clusters equals sign 3. Model.fit. Customer underscore shopping underscore data. Finally, let's mention principal component analysis, or PCA. This is also an unsupervised technique used for dimensionality reduction. These algorithms are not just theoretical concepts. They power many apps you use daily. Let's look at real-world examples. Linear regression, our simple line-fitting tool, is used extensively in finance and economics. Businesses use it to predict sales for the next quarter based on their advertising budget. Real estate companies use it to estimate house prices based on features like area, number of rooms, location. It's a go-to for forecasting linear relationships. It helps make data-driven business decisions. Logistic regression is the workhorse of classification problems. Email services use it to filter spam. It inspects features and computes the probability an email is spam. In healthcare, it predicts disease from symptoms and reports. Banks use it to estimate loan default risk. Anytime you need a yes or no answer, logistic regression is a good start. Decision trees are popular because they're easy to interpret. You can literally see the decision-making process. They're used in customer support. A tree can guide a customer through troubleshooting by asking questions. In business, trees help with churn prediction. Who might leave? Understanding the rules shows why customers leave, so companies can act. For example, if the tree flags poor network coverage, the company can improve the network. What about unsupervised methods? K-means clustering is a marketer's best friend. Online retailers use it for customer segmentation. They group customers by browsing history, purchase patterns, demographics. That enables targeted campaigns. One group might get electronics promos, while another gets clothing offers. Similarly, PCA is used in facial recognition image processing. It reduces many pixels to a few principal components, making face matching much faster and more efficient. The field of machine learning is evolving at an incredible speed. What seems like science fiction today might become a part of our daily lives tomorrow. One of the biggest trends is the rise of deep learning, a subfield inspired by the human brain. Neural networks have many layers and learn extremely complex patterns from vast data. They are the power behind self-driving cars. They power Alexa. They power Google Assistant. They power image generators like DALL-E. They power language models like ChatGPT. The future, even more powerful and accessible models. Democratization of AI is changing who can build models. In the past, it required PhD-level expertise and massive computing power. Now, AutoML is automating many of the complex steps. Cloud platforms from Google, cloud platforms from Amazon, cloud platforms from Microsoft. These tools let developers and business users create and deploy AI. More people solving specific problems with AI. Machine learning will tackle some of humanity's biggest challenges, accelerating drug discovery, developing personalized medicine tailored to genetics. In agriculture, machine learning enables precision farming. Drones collect data over fields. Sensors collect data in the soil and on plants. Monitoring soil health. Monitoring crop conditions. Algorithms help farmers use water and fertilizers more efficiently. For climate change, better climate predictions. And optimizing energy grids for renewable sources. The potential for positive impact is immense. With great power comes great responsibility. As ML integrates into society, we must address ethical challenges, data privacy, algorithmic bias, the impact of automation on jobs. The future isn't just more powerful algorithms, it's responsible AI, fair AI, transparent AI, systems that benefit all humanity. As citizens, it is important for all of us to be a part of this conversation. So, we have covered a lot of ground today. We started with the basic question: what is machine learning? We journeyed through its main types, core concepts, popular algorithms. We saw how these powerful tools are already changing the world around us. I hope this discussion has demystified the topic for you. Machine learning is not an unapproachable black box. It's a logical field built on simple, understandable principles. It's a tool you can learn to use. Remember the analogy of teaching a child? Learning ML is similar. It might seem daunting with new terms and concepts. Don't be discouraged. Start small, be curious, learn step by step. You don't need to be an expert overnight. Play with a simple dataset. Build a basic linear regression model. Train your first model and see a prediction. It's rewarding. It will motivate you to learn more. The internet is full of resources, online courses, YouTube tutorials, blogs, open source communities. A journey of 1,000 miles begins with a single step. First step, download a dataset, or run your first line of Python. Embrace learning. Make mistakes. That's how you learn. Ask questions. Be curious. Find a small project and apply ML to it. The world needs more people who understand this tech. Build a career in it. Use it to grow your business. Be an informed citizen. Learning ML is a valuable investment in your future. You've taken the first step today. Keep going. The journey is long but full of discoveries. The power to create, to solve problems, to innovate, more accessible than ever. Your ML journey begins now. All the best. Jai Hind.